Okay, today we are actually in 4.4 using the first fundamental theorem of calculus, okay? So when we are given an integral, our lower bound is a, our upper bound is b, and we are integrating some function with respect to x, okay? So the first fundamental theorem of calculus says we are going to estimate that antiderivative at the b value and subtract from it the antiderivative evaluated at the a value, okay, which is the upper bound and then the lower bound. So example 1, we've got from 1 to 2, and we are integrating x squared minus 3 with respect to x, okay? So the antiderivative of x squared, remember, you're adding 1 to the power and making that same sum the denominator. So the antiderivative of x squared is x cubed over 3, and the antiderivative of 3 is 3x, and we are estimating that from a low value of 1, a high value of 2 to a low value of 1. So what this will look like, and you can enter into your calculator by using your second enter thing, okay? It'll be that evaluation minus this evaluation right here, okay? So in your calculator, you're going to first store your value of 2, okay? So 2, store x, enter, and then enter in your x cubed over 3 minus 3x, and that gives you a value of negative 10 over 3 when you put a 2 in there. Now we're going to enter a 1 store x, enter, second enter, enter, and you will get a negative 8 over 3, okay? So negative 10 thirds minus a negative 8 thirds is the same thing as negative 10 thirds plus 8 thirds, which gives you negative 2 thirds. Okay, so we'll do the same thing with example 1b. Okay, so example 1b is from 1 to 4, 3 times the square root of x with respect to x. So we're going to simplify this a little bit. Remember that 3 is like our constant multiple. So we can pull that out front, and what we're integrating is x to the 1/2. So your rewrite is required. So 3 times the antiderivative of x to the 1/2, we're going to add 2 over 2, so that is going to be x to the 3/2 over 3/2. And we are integrating that from 1 to 4. So remember, we're going to take the denominator of 3 over 2, and we are going to put it out front and flip it upside down. So in our simplifications here, we are going to get it down to its simplest form, which is that one right there. Okay? Now, you enter a 4, store x, enter, and then enter in 2x to the power of, you could either do 3 over 2 or 1.5, it doesn't matter. And you get, when you put a 4 in for x, you get 16. And when you put a 1 in for x, you get 2. So your area between 1 and 4 of that curve is 14. Okay, so moving along. The antiderivative of secant squared from 0 to pi over 4 with respect to x. Okay, the antiderivative of secant squared is tangent. And notice we drop off the plus c here because we've got values at which we are evaluating our antiderivative. So the tangent of pi over 4, you're going to have to use your unit circle and do sine over cosine, is 1. And the tangent of 0 is 0. So our value or area between 0 and pi over 4 of the curve secant squared is 1. Okay? Now, for example 2, okay, we're first of all going to investigate what this graph actually looks like, okay? 2x minus 1 under an absolute value. So we have 2x minus 1. So we're going to take that argument, set it equal to 0, and that we get x is 1/2. Okay, so I'm just using this to graph. So when x is 1/2, so let's say this is 1, 2, and 3. When x is 1/2, y is 0. Okay? So the graph is right there, and it looks like this. Okay? Well, if we're integrating from 0, which is right here, to 2, which is right here, we have two different areas that we're integrating. It's going to be this right here, that little area right there, and this area right here. So what we have to do is add together the two areas. Okay? So for this area right there that we'll call area 1, we are integrating from 0 to 1/2, okay, of the curve negative of 2x minus 1. And that negative is because the branch of that absolute value there is negative. The slope is negative. Okay? So the rewrite of that is from 0 to 1/2 of negative 2x plus 1 dx. Okay? And then the antiderivative or the integration of that is going to be negative 2x squared over 2 plus x from 0 to 1/2. Now, of course, those 2's will cancel out. Okay? And then the second area that we're integrating starts at 1/2 and ends at 2. And that branch of the absolute value is positive. Okay? So we will end up integrating and getting 2x squared over 2 minus x, and our 2's will cancel, from 1/2 to 2. Okay? So let's see. I want to copy and paste. Hold on, bear with me, guys. And then x squared minus x. Okay, that's what I wanted to do. Just trying to copy it, and it was taking more time than it needed to. So we are going to work on this right here. Negative x squared plus x from 0 to 1/2. And then to that, we will add. So what we're doing is adding those two areas together. And then x squared minus x from 1/2 to 2, okay? So obviously when you put a 0 up in here, you're going to get a 0, okay? So we just need to enter in 0.5 and store that, and then we will be entering in negative x squared plus x, and we get 0.25. That's when you enter in 1/2. Okay? Then we'll do the same thing down here. We'll first store a 2. Okay, we'll first store a 2 and then enter in x squared minus x, and get, when you enter in a 2, you get 2 minus, now what we're going to do is store the 1/2, and then second enter, enter, and get a negative 0.25. So that's 2 plus 0.25 is 2.25. So what we'll do now is add both of those areas together. 2.25 plus the 0.25 to get a total of 2.5. So that's a really good example of why you actually need sometimes to draw in your graphs. Okay, so you can see that the graph was drawn to the left of example 2 and the area then that we are that we're shading in and integrating. Okay, so example 3, exactly the same thing. As long as you're given an equation, sometimes you need the graph, sometimes you don't. In this case, it's just a polynomial. So you don't have your branches changing slope like you do in an absolute value. Okay? This is just a parabola. Its domain is all real numbers, and there is no point of discontinuity. There is also no point that you've got any place where it is not differentiable. It's just a regular old parabola. So the antiderivative of 2x squared is 2x cubed over 3. The antiderivative of 3x is 3x squared over 2. And the antiderivative of 2 is 2x, and we are evaluating from 0 to 2. So you get the idea. We're going to enter all of these into our calculator. 2, store x, enter, and then one value at a time. 2/3 x cubed minus, and I'm just going to do 1.5. 1.5 x squared plus 2x. And when you enter a 2 in there, you get 3 1/3, which is the same thing as 10/3. Okay? So when you enter a 2 in there, you get 10/3. Now, if you put a 0 in there, obviously all of those terms go to 0. So that is your area. Under the curve of that parabola from 0 to 2. Easy stuff. Okay. So example 4, the mean value theorem for integrals is, it states, and I'm reading from the text, the mean value theorem for integrals states that somewhere between the inscribed and circumscribed rectangles, so look to the left and you see that drawing, figure 4.3, you get a rectangle whose area is precisely equal to the area of the region under the curve. So if you notice, the blue area that overhangs the curve and the pink area that's underneath the curve, those are exactly the same, okay? So you're finding your average height. That's what the mean value theorem for integrals tells you, is the average height of a rectangle. And then, of course, you've got the area in between which you're integrating. So you have a formula for that, okay? So let's use that formula. Okay, that is the formula for the mean value theorem for integrals, okay? So for example 4, it says finding the average value. Obviously, mean is the same thing as average, so we're using this formula. So find the average on the interval from 1 to 4 of 3x squared minus 2x. Okay, so our A value is 1, our B value is 4. So 1 over 4 minus 1 is 1/3 times, here's our function, whoops. Okay, so now we're going to integrate 3x squared minus 2x. So 1/3 times, so the antiderivative of 3x squared is 3x cubed over 3, and those 3's will cancel. And the antiderivative of 2x is 2x squared over 2, and those 2's will cancel. And we are evaluating from 1 to 4. So we're evaluating 1/3 x cubed, yikes, excuse me, x cubed minus x squared from 1 to 4. Okay, and obviously that is a very simple thing now. You're going to evaluate 4 cubed minus 4 squared, which is 64 minus 16. So that would be 48. And then when you put a 1 in there, you get 1 minus 1, which is 0. So 1/3 of 48 is 16. Okay, so that is your mean value for that particular integral between 1 and 4. Okay. So look at the picture, okay? The average value or the mean value is 16. Now, here's what this tells us, okay? So we're looking at that curve, and I'm not going to draw out the whole thing. I'm just going to draw the rectangle that we're given from 1 to 4. Obviously, the width between 1 and 4 is 3. Now, we just found the average value or the average height of that rectangle is 16. So this should be like mind-blowing, because we just found we could find the area to be 48. Because remember, we had 48 as the area under the curve between 1 and 4 before we divided it by 3. So the area of this whole thing right here, when you integrate it and then evaluate it between 1 and 4, is 48. Okay, that's the area. When we do it like this, and we find the width, which we're given, then we find the average value, which is the height. When you multiply, you get the exact same area. That is very, very cool. Okay, so that is your average height or your mean value theorem for integrals. Okay, now moving along, we are going to look at example 6. All right, so example 6. Oh, this one gets tricky. Okay, for example 6, okay, we've got the second fundamental theorem of calculus, okay? So if you recall, say we've got this function right here. Okay? If we want to find the derivative of that function, we get 12x cubed. So remember, the very first thing that we learned about finding derivatives is that that derivative gives you a slope formula for finding the slope at any x value on your curve. Okay? When we use the second fundamental theorem of calculus, what that's giving you is a general formula to find the area under a given curve at any particular value of x. So the second fundamental theorem of calculus gives you, it's kind of the same idea as the first derivative. First derivative gives you a slope formula. Second fundamental theorem of calculus gives you an area formula for any value of x under the curve. So, for example 6, we've got f of x from 0 to x cosine t dt. Okay? So you can disregard the lower value, and we'll get to that when you've got a value other than just x, but we'll disregard the lower value, and all we do is plug in. All we have to do is plug in the x for the t. So we would be evaluating cosine x dx. And then once we have that antiderivative formula, which is the antiderivative of cosine is sine x plus c, this right here would give us the area under this curve right here at any value of x that we pick. Okay? So if we wanted to do, say, the example gives us at x equals 0, pi over 6, pi over 4, pi over 3, and pi over 2. Okay? If we wanted to evaluate sine x, we would just do all you would do is plug in your values of x. 0, pi over 6, pi over 4, etc. Okay? And you would be able to determine the value. So you can see underneath example 6, you've got your 0, pi over 6, pi over 4, and then all you're doing is plugging in. So x equals 0. The sine of 0 is 0. at x equals pi over 6, the sine of pi over 6 is 1/2. Okay, so again, when we use the second fundamental theorem of calculus, we are finding a formula, a general area formula that will give us the area under that particular given curve at any value of x. Okay, so for finding the next example, example 7, okay, it says, using the second fundamental theorem of calculus. So it says evaluate the derivative, which is the exact same thing as capital F of x, of the curve between 0 and x of t squared plus 1 dt. So the first thing that we're going to do, and I'm going to throw in a little bit of an extra thing, let's evaluate that at x equals 4, x equals 6, and x equals 10. In other words, the area under the curve from 0 to x can be found using the second fundamental theorem of calculus. Okay, so the formula is going to be the square root of x squared plus 1 with respect to x. Okay, so we're going to find the antiderivative of that. Oh, and you know what? We don't have the means to do that yet. We have not yet done the integration by parts. So let's do another one. From 0 to x of, let's say, t squared minus t with respect to t, and we are going to then find the area at x equals 1, 3, and 5. In other words, the area under that curve at any given value of x, and I picked these. Okay, so first thing we're going to do is replace the t with an x. So we are integrating x squared minus x with respect to x. Now, when we do that, the antiderivative of x squared is x cubed over 3, and the antiderivative of x is x squared over 2 plus c. Okay? In other words, that gives, and we don't need the plus c. Okay? In other words, what this is an area formula that we can use for any value of x to find the area under that curve. Okay, so graphically, let's draw the curve. So what I'm going to be graphing is our basic t squared minus t which looks like something like that. Okay, not very neat, but there you have it. That's the curve, okay? So we are going to be plugging in a 1 first. So here's x equals 1 right there, okay? When we plug in a 1, we get 1/3 minus 1/2. So let's find that area. That gives us negative I'm changing my decimal to a fraction. Negative 1/6. In other words, from 0 to this x value, right there, that little purple area that I just colored in there is negative 1/6. Okay, now we're going to do the same thing with from 0 to 3. Okay, so here's 0 and here's 3. When we plug in a 3, 3 cubed is 27 over 3 minus 9 over 2. So 27 over 3 is 9. So 9 minus 4.5 is 4.5. In other words, from here from 0 to 3, the area under the curves is 4.5. And then, of course, if our curve went more and more into bigger y's and bigger x's, we could get then the curve from 0 to 5. Okay, so that's what the second fundamental theorem of calculus does for us. Actually very cool. Again, remember, the second fundamental theorem of calculus gives us an area formula that we can use to find area under a curve for any x value that we plug in, from 0 to whatever, or 1, or whatever the beginning a value is. Okay, now using the second fundamental theorem of calculus for example 8. Okay, so we've got from pi over 2 to x cubed of cosine t with respect to t. Now, because that x cubed is not just an x, we have to use the chain rule. Okay, so the first thing that we're going to do is differentiate x cubed. So the derivative of x cubed is 3x squared. Okay? Now, what we're going to do is plug in. So this is step 1. If your upper bound is not just an x, you have to find the derivative of it. Okay, that's step 1. Step 2 is to now plug in that upper bound for t. So we get cosine x cubed. Okay, and then the formula finally will be the product of these two things right here. So we would get 3x squared cosine x cubed. Okay, and then integrate. Not integrate, then you can plug in any value of x you want. Sorry. So when we have an upper bound that is not just an x, we have to take the derivative of the upper bound, then plug in the upper bound into the function, and then multiply them both together. So that gives us the function, the original function. Okay? Okay, for this particular example, what I want to point out is the differences between what's in example 7 and what's in example 8. Okay? For example 7, actually, let me go back to the one that I did right here. Okay? when we were evaluating, we were looking for f of x, okay? What that is that is going to be our formula that we can use to find the area under the curve at any x value, okay? That is our f of x. Now, the difference between that and number 8, example 8, is we were asked to find capital F prime. Now, capital F prime is the original function. That is the original function, which we got as 3x squared times cosine of x cubed. Now, that is our f, capital F prime. If we wanted to find the area, the general area formula, we would actually have to find the antiderivative of the original function. And again, that is something that we are not yet able to do. That's the antiderivative of the original function. That is the difference, okay? The capital F prime is the derivative of the antiderivative, which is your original function. Just capital F is the antiderivative. So in other words, if we wanted to find out what the general area formula is for this curve up here at the top, we would have to be able to integrate now 3x squared times cosine of x cubed with respect to x. Now, again, that is something that we are way not ready for yet. That would be using integration by parts, which is the antiderivative formula when you've got a product that you're integrating, okay? And we haven't learned that yet. So again, capital F prime is the original function. If you want to find the general area curve or area formula, you need to be able to find the antiderivative of capital F prime, which is just capital F. Okay, there is a huge difference. So this is capital F prime right here. If we were able to integrate that, we would just get capital F. So let's do an example here. Let me just erase all of this. Okay, so let's do a basic one from 0 to x of cosine t with respect to t. Okay? Now, our f prime, capital F prime, is just throwing in the x for t. Okay, that's our capital F prime. Capital F is then integrating that. Okay, again, there's the difference. Okay, capital F prime is just throwing in the x for the t. Capital F is actually integrating that. Again, very, very important difference. So once you find the antiderivative of capital F prime, then you can evaluate at given values of x. And again, when you're using the second fundamental theorem of calculus, you can leave off the plus c because that's just a formula that we can now use. So when x is equal to 0, the sign of 0 is 0. When x is equal to pi over 2, the sine of pi over 2 is 1. So here's the curve. Okay, we got pi over 2, pi, 3 pi over 2, and 2 pi, and we're graphing cosine. So that's the cosine curve, okay? If we're looking for the area under the curve between 0 and 0, well, obviously it's 0. If we're looking for the area under the curve between 0 and pi over 2, we're finding this area right here. Okay, and that area is equal to 1. Now, if we were finding the area between 0 and x equals pi, this is the area that we are finding right there. So the sine of pi is equal to 0, which means that the area above the curve and that shaded area below the curve are exactly the same thing. So the upper positive minus the lower negative gives you 0. Okay? So again, capital F prime is not the same thing as capital F.